So here we're continuing to build our theorem 215, which is our collection of tools for showing that functions are measurable. So assume you have a measurable space and assume you have two measurable real valued functions on it. Last time we ended with proving that their sum, or any linear combination, is measurable. Now we're going to focus on the product. So quick sort of beginning of lecture reminders. Measurable space, that means this is a set and this is a sigma algebra on the set. And then these two are measurable functions. To be clear on what is meant by measurable function, we can specify the sigma algebras that we're talking about. So the given one on X and the Borel one on the reals. And to say they're measurable functions means that the preimage of any Borel measurable set here is going to be a measurable set here, just meaning that the preimage of any set from this class is going to be a set from this class. Then we want to show the product is measurable. So there's a trick to this, which allows us to reduce the problem to showing that the square of a measurable function is measurable. So here this is a pointwise product, this is a pointwise square. And I'll describe first why this is sufficient. So eventually I'll fill this in, but then we are done if we prove the square of a measurable function is measurable, because the product can be written in terms of squares of measurable functions. So like if I take f plus g squared, then that expands to give f squared, which I can get rid of, g squared, which I can get rid of, and then what's left over will be the cross term 2fg. So then if I just divide everything by 2, that's fg. So the pointwise product is this. And we already know that then we are done by part 1. Or I think it was part 2 actually. Part 2 tells us the linear combination of measurable functions is measurable. So if you know squares of measurables are measurable, and things like f plus g are measurable, then using part 2, you get that this is measurable. Okay, I think everyone sees what I'm talking about. So let's just prove that f squared is measurable, and therefore also g squared, and therefore also f plus g squared, and so on. So square of a measurable is measurable. So here's proof of the claim. And for this, we can just think about, in terms of composition, what's happening when we look at the pointwise squaring of a function. So f squared is the composite, the following composite. Start with x, then do f, and then you end up with real numbers. Then do the squaring function, so the function that sends a real number x to its square. Now, in each position along the way here, there's a sigma algebra involved, right? Here we've got A, here we've got the Borel sigma algebra, here we've got the Borel sigma algebra. And we're interested in the measurability of the composite, right, from here to there. We know that if you compose measurable functions, then that gives you something measurable. F is measurable by assumption. Now, can we prove that this is measurable? Well, it's continuous, right? R is a metric space, the reals are a metric space, and that's where they get their sigma algebra from. It's the Borel sigma algebra. Continuous functions are measurable when you're talking about the Borel sigma algebra. So that's it. So the rest of the argument is just this is a measurable function because it's continuous. All right, next one. So we're done looking at products. Now let's look at quotients. So again, start with a measurable space. Suppose you have two measurable functions on that space, real valued functions, and assume that one of them can work as a denominator in a fraction. So assume that it's just not 0 ever. Then you can define the pointwise quotient f divided by g and this should be measurable. Now, a quotient is a product of f with 1 over g, right? So since we already handled products in part 3, so by 3, it is enough to just handle 1 over g, right? It is enough to show that the function, the pointwise reciprocal of g, 1 over g, is measurable. Now, if I'm going to follow the same approach as before for the other parts, then here's what I would do. Start with x. So I'd say, look, 1 over g is this composite. And I'll try to express it as a composition of measurable things. So start with x, first do g, then you end up with real numbers, and then take the reciprocals. So apply the reals to reals function that sends x to 1 over x. And then g is measurable by assumption, right? And then this function is continuous, because it looks like a nice function, right? So it's continuous, and continuous functions are measurable, and so we're done. Composition of measurables is measurable. Okay, but hopefully you are sensing that something is off here. Can you see the problem? So here's the problem that I hope you're noticing. This does not work as a domain for this function, right? The function x goes to 1 over x is not defined on all of R. So even though g never takes on the value 0, I still cannot express g as this kind of composition. That just doesn't make sense. So how can I repair this and still get the argument to work? Because it'd be really nice if I don't have to work with the ugliness of taking reciprocals and thinking about whether that treats Borel sets nicely. I really don't want to think about doing that. Instead, I'd rather rely on previously done work where I know that the x to 1 over x function is continuous. If I can just replace this with a domain where it's defined, I'd rather rely on previously done work. So what to do? Well, if g really never takes the value 0, as I'm assuming here, then I could view g as a function x to r with 0 deleted, right? So I could view g as this kind of function. I can always shrink the codomain to be anything that contains the range. So this is valid because of this assumption. Now, some people might complain that if I change the codomain, then I should probably give this mapping a different name, since it has a different codomain. And if you're one of those people, then I respect that. I'm just going to call it g still. But yeah, something is kind of different when you change the codomain. It's good to pay attention to that. But it's still the same like mapping, right? Or it's the same. It takes the same values at the exact same points. Okay, so that depends on what your opinion is on what functions are. So anyway, I'm going to call it g. So I can do this. Then I can definitely apply this x goes to 1 over x function. So I can compose with this. And okay, that's better. This is a continuous function from here to there, right? And actually, when I say 1 over g is measurable here, when I take the pointwise reciprocal, or when I take this pointwise quotient, what is the codomain that I'm talking about? So let's make the statement of the theorem clearer. We'd like not to change the codomain. So we'd like to still think of these as real valued functions. Yeah. So we'd like to keep it like this. So actually, I would prefer to just put r here. And that's perfectly fine. The function that takes reciprocals, x goes to 1 over x, can be thought of as a function with this domain and this codomain. That's fine. And let's now discuss the sigma algebras that are getting involved. So here we have fancy A, the sigma algebra we're given for X. Here we have the Borel sigma algebra on R. What about here? What's the sigma algebra on this? Well, this is a subset of R, right? So as a metric space, it's a subspace. It has its own restricted metric, and so it has its own Borel sigma algebra. So that's one way to think about the sigma algebra on this thing, is that it's the Borel sigma algebra on this metric space. That's one way to think about it. And if you think about it this way, then what do we have here? A continuous function from one metric space to another, and where we put the Borel sigma algebras on the metric spaces. Since it's continuous, it's measurable. So if you think about the sigma algebra on this set in this way, then due to the continuity of this, it's measurable. Measurable because continuous. Okay, but is G measurable? I mean, G was assumed to be a measurable function by assumption, but hang on. G was assumed to be a this measurable function, right? That was back when we were thinking of the codomain of G as R. So now that I've shrunken the codomain down and I'm putting this sigma algebra on it, is G still measurable? So you see why I think it sometimes is useful to give mappings different names when you change the codomain. It's a little weird to ask, is G still measurable? Well, if there were a possibility that it not be, then I probably shouldn't call it G also after I make this change, right? Okay, anyway, so after I make this change, is this new version of G, is it also a measurable? Is it this thing measurable? So in other words, the question is, if I take a Borel subset of this space, so an element of this, and I take the preimage under G, then will I get a measurable set, an element of fancy A here? And in this case, it's really easy, actually, to answer this because this is an open set. So it's a Borel set. So R with 0 deleted is a Borel set. And so that means the collection of Borel subsets of this thing is just a subset of the collection of Borel subsets on R. So that does not always happen, remember? If you take a metric space and then take a subset of that metric space, it's not always true necessarily that the Borel sets on the subset are the same as the Borel sets on the... It's not always true that the Borel sets on the subset are even Borel sets on the large set. Just like it's not always true that the open sets in a subspace are always open sets in the larger space. But here it's true, since this is open and therefore Borel. So if I take something from this yellow set here, a Borel subset of this thing, then it is a Borel subset of R, and since G is measurable in the this thing sense, when I take the preimage, I get something in fancy A. So then this is measurable by assumption. So the assumption that G is measurable does carry over to tell us that this new version is also measurable. And yeah, so let me get rid of this part. So yeah, I mean that's it. So we're looking at 1 over G is this composite of measurable functions, so it's measurable. Okay, so this took me on kind of a tangent here. Our discussion back here about changing the codomain of G, I think brings up an interesting question. If you have a measurable function and you shrink the codomain in a way that you can, so that it still is a valid new codomain, can that ever affect measurability? So let's just look at this quickly. Suppose you have a function, so this is a new context. Suppose you have a function G from x to y, and x and y are measurable spaces, say with these sigma algebras, fancy A and fancy B. And suppose that E is a subset of y which could also work as a codomain for G. So what I mean is it contains as a subset the range of G. Then let's use I to denote the inclusion e to y. So there's a sigma algebra on E, which is a very natural one to use, which is the pullback of the sigma algebra on Y under the inclusion. This is one we have looked at before. It's like taking all of the measurable subsets of Y and then intersecting them with E to get measurable subsets of E. Now let's look at G with the codomain modified. And for this particular question, I'm going to actually give it a different name for the moment. So let's call it G bar. So G bar is going to be G except with the codomain being E. So same domain, same formula, or whatever, you know, G bar at any input equals the same thing that G does at that input, but it's just a mapping from X to E. So we're changing what the codomain is. So here's the main question. If G is AB measurable, so remember G maps X to Y, so if G is AB measurable, then is G bar a pullback of B to E measurable? And I have looked at this a little bit and pretty quickly got yes. So over here in this particular situation, we got a yes, but we sort of thought about this as we used the fact that the E, the set we're restricting the codomain to, is a Borel set, or is a measurable set. Here, we are not making that assumption. I'm just saying in general, the answer will be yes. So here's my argument. Take any measurable subset of E, so meaning with respect to the pulled back sigma algebra on Y. So let's call that S, any measurable subset of E. And then my goal is to show you that if I take that measurable subset of E and pull it back along G bar, then I get a measurable subset of X, right? So if S is a measurable subset of E, then by definition of this pullback, it's the intersection with E of a measurable subset of capital Y, right? So it's B intersect E for some B and fancy B. So then look at the preimage under G bar of this set. Can we show that it's a measurable subset of X? Well, it's the same as taking the preimage under G, right? The things in the domain that G bar maps to S is the same as the things in the domain that G maps to S. They have the same domain, right? And they operate the same way. And then that's the same as actually taking the preimage of B. So let me give a quick argument for that these are equal. So for this equality, this inclusion is obvious, I would say, since S is B intersects something, so S is a subset of B, so this inclusion is obvious. And then for the other inclusion, let me talk through it. If you have some point in here, so something that G maps into B here, then since G maps it into B, and since the range of G is assumed to be a subset of E, G also is known to map it into E, and therefore G maps it into S. So yeah, these equalities are pretty easy to check, and yeah, so the preimage under G bar of any measurable set is measurable. So this is a general yes. So general principle, if you restrict the codomain of a measurable function, it's going to be measurable, assuming the sigma algebra uses is the pullback one. Is that what we were using here? I didn't actually write pullback sigma algebra, right? Here I wrote Borel sigma algebra on this thing. But it's actually the same, right? This is something we've discussed before. So you can, this thing is the same as if you took the pullback of this one, where I is the inclusion of this set into there. So yeah, it is needed to have this be a Borel set in order to have this subset statement here. But even if this is not a Borel set, we still have that this is the same as this, and that the measurability of G is not harmed by shrinking the codomain down to this. Okay, so that was just probably not necessary, but kind of interesting. interesting, and I should say relieving, that we don't have to worry about shrinking codomains so much. All right, there's a little more to this theorem, and we'll do part 5, which is about pointwise limit of measurable functions in the next video.